All right, last but not least, let's talk about confidence intervals around the variance, or really the standard deviation. I mean, we use the variance a bunch. I don't want to say, oh, it's useless and it only gets us through to the standard deviation. That's not true. There's tons of parametric statistics that uses the variance, that you have to have the variance for, and they're very clever. But by and large, what we need this for is to be able to figure out the standard deviation. Now, I'm not going to get too crazy in this section because there are some relatively advanced topics going on here. I'm going to give you formulas. I'm going to show you how to use them, and we'll talk about them. Now, remember, variance distributes itself. All right? Remember, first and foremost, sample variances are an unbiased estimator, right? And they distribute themselves. If I do a whole bunch of them and I take the average of them, then I end up with this weird curve that does this. All right, now it's on, we have an x and a y. It's not just like we only care about the x-axis like we did with the others. This should be more curved, by the way. That looks a little too linear. Looks like this. It is not a normal curve. It is an asymmetric curve. And the reason is, think about it. We know for a fact that variances are always positive. They have to be. They have no choice. This is sometimes referred to as a chi-squared curve. Chi-squared. So chi-squared. It's called the chi-squared curve. It's not symmetric, okay? And this thing changes just like t. This thing will change with degrees of freedom. As degrees of freedom increase, so this is dependent on degrees of freedom. Let's change colors real quick. Let's say that, well, let's go back to black. Let's say that this guy right here is degrees of freedom equal 10. All right? What would happen is, as degrees of freedom increase, what you end up with is a curve that looks far more normal, even though it can't be because it's cut off over there. It can't go all the way to negative infinity theoretically. But let's say that this is degrees of freedom of, say, 50. Now, the problem with this family of curves, just like we had with the t-curves, the problem is that it's not symmetric. So remember back in the day when we were putzing around, and all we did, if we wanted to figure out confidence intervals around proportions and around means, we took p hat minus error and p hat plus error, or we took x bar minus the error, because the error was the same on both sides because they came from the normal curve, and x bar plus the error. In other words, these guys were always the same value. These guys were, wait, I didn't mean to write it like that. Try that again. Sorry. I wrote my arrows the wrong way. These guys were always the same values. And these guys were all the same values because they came from a curve that was symmetric. So I got a value here and a value here. Well, that's not going to work here, because this curve doesn't work like that. So when I go to find my values, I got to get a little more complicated, okay? All right, I'm going to show you how to do this, and we'll do it almost exclusively from the chart. Now, before we do that, I know that I run a risk of confusing you here, but we're going to use just the formula first and foremost. I'm going to give you the chi-squared formula. So chi-squared is equal to n minus 1 times the standard deviation of the sample divided by sigma squared. That is the formula that produces this curve, okay? So if you think about it, if I'm trying to find a confidence interval around sigma, watch what happens. A super simple cross multiplication, I get sigma squared equals n minus 1 times s squared divided by chi-squared. Now, this chi-squared value is where we get our critical values from. All right, and we're going to use our table to do that. Now, again, the asymmetry of this thing is kind of a pain in the butt. And I'm going to give you the overall formula right now. So this chi-squared creates this family of curves. And then we did a little algebra like we did before when we were trying to figure out the error values for means and for proportions. The formula for this is actually sigma squared is going to live between, now it's going to be n minus 1 times the sample standard deviation squared divided by chi squared, except this is going to be the chi squared value on the left. Now think of this value right here as the chi squared value on the left. Then I'm going to have n minus 1 times s squared, and I'm going to divide that by the chi squared value on the right. And we have to delineate these. We have to separate them because of that asymmetry. So this is chi squared on the right. Now, let me draw this out a little bit for you guys real quick, just so you can look at this. I want to make sure you get this. Even though it's all formulaically driven, nothing's too crazy. All right, here's my chi squared. Okay? Now again, asymmetry. Ooh, that's a badly drawn chi-squared. It looks more normal. That's a bummer. That's not what I wanted. Let me redraw this guy just a little bit so we get a little more exaggeration. Okay? And let's say, for example, that I want a 95% confidence interval. Now, here's what I'm going to have to do. I'm going to have to figure out my chi-squared on the left and my chi-squared on the right. Now notice the areas here, what I need is, I'm going to need 0.025 worth of area on this guy, and I'm going to need 0.025 area on this guy as well. But because the areas don't look the same, I mean, just by looking at this curve, it's confusing. So what I have to do is I'm going to dig in on my table, and my tables, I'll show you guys how to do this. Now the most important thing that you get out of this is that the hardest one to find is this guy right here. So think about this. If I'm doing a 95% confidence interval, basically the way the tables work is they always give areas to the right of the critical value. So when I go to look for the area to the right of the critical value, and really theoretically this goes into infinity, so this 2 would go into infinity, all of this is 97.5% or 0.975, but that includes all of the area all the way to infinity. Now when I find this guy, it's easy. I just go dig around for 0.025 in my chart, just like the other charts work. Now, let's do that right now. We are going to find these critical values, this chi-squared left and this chi-squared right. Just now, I'll change the color of my pen, and we'll go to a chi-squared table. Let's see if I can find a chi-squared table around here somewhere. Man, I got all kinds of stuff open, don't I? All right, you ready? Oh, there's a chi-squared distribution. Look at this. All right, well, I'll show you both of them. Here's the shape of the curve. Right? This is what it looks like. These are my degrees of freedom. Remember, degrees of freedom come into play whenever you're talking about a sample standard deviation. You have to respect that. Okay? And then check this out. Okay. I suppose I should come up with a degree of freedom for this guy. So let me pop him open real quick. Bamboo paper. Let's say that, I don't know, let's make degrees of freedom, let's make it 20. All right, now watch how this works. It's not so bad. I'm going to find my chi-squared left, and I'm going to find my chi-squared right. And watch what happens. So let's see. If it's 95%, that means that if my chi-squared left is going to have an area, this tail over here is going to be 0.025 to the left. But I want everything to the right, which is 0.975. But looky here. Right here it says 0.975. So I go down, what did I say my degrees of freedom were? It was 20, wasn't it? Let's pop that thing back up again. Degrees of freedom are 20. So the value on the left is going to be 9.591. 9.591. And the value on the right is going to be the value that produces 0.025. See? This chart gives it to me to the right. So 0.025, I stumble down to degrees of freedom to the right, which is 34.170. Now you may say, wow, Ripley, those are some big numbers. 34, what was it? 34, where the heck am I? 34.170. So 34.170. I'll just write it as 34.17. Okay? Why are these so big? Why are they so huge? Well, we're talking about variance, right? Variance is a value squared. So any number, if you've got a variance if you've got a standard deviation that's greater than 1, then when you square it, you're going to get a bigger number. That's why these numbers are so huge. Now, let me show you. This is I used that one because I wanted one with a nice picture on the top. But look, we'll get exactly the same values. Look, so here's my degrees of freedom. Down the column, across the rows is the area to the right of the value. At 0.975, if I go down to degrees of freedom, I get 9.591. If I go to 0.025 and I go down the column, I get 34.170. So that skill right there, in and of itself, is the most important skill that you need to be able to do. Because really, guys, look at the formula. I mean, the formula is pretty straightforward. And we'll do one of those guys here in just a second. Okay? All right. Hey, one thing that I just realized that I screwed up on that last page was that your variance here is going to live between, we got n minus 1 times s squared divided by, and then n minus 1 times s squared divided by. I actually wrote it as chi squared over the chi squared, the left chi squared, this should be the right. If you think about y, we'll talk about that here in just a second. And this is on the left. You guys, this is a bigger number. Remember, if I go back, this is a bigger number. So it's clearly going to produce a fraction that's smaller. This is the smaller number, so it's going to produce a fraction that's bigger. Clearly, I apologize about that. I also wanted to make sure that we make mention is, especially for what we're going to use these for, what we really want is we want sigma. Well, I'm not afraid. If this gives me the confidence interval for sigma squared, then I just got to take the square root of everything. So I end up with the square root of n minus 1 times s squared divided by chi squared on the right, because it's the bigger one. And this is the square root of n minus 1 times s squared over chi squared on the left, because it's a smaller one, so I'm going to produce bigger numbers. All right, but just like everything else, I want you to have this aching suspicion that you're not meeting assumptions. All right, the assumptions for being able to build a chi-squared, what am I saying? A confidence interval around variance and thus standard deviation, which is what we're really interested in. The first things first are, it's got to be an SRS. In other words, when you gather your data, it's got to be a simple random sample. So you got to go and you got to randomize, randomize. That's our mantra pretty much too. And this is probably the most limiting one. Is the population has to be, it's got no choice, has to be normally distributed. If it isn't normally distributed, we can't use this technique. We have to use far more complicated techniques. All right, and this is an intro to stats class, so we're not particularly worried about that. But the population has got to be normally distributed for us to even be able to talk about this. All right, now I'm going to walk you through just really quickly. I'm going to walk you through one of these problems because really it's computational. It's difficult to do on a calculator or on a computer unless you have programs that are geared specifically for it. So let's just real quick go through this guy. Let's say that I'm not even going to try and make up a story for it. Let's just watch what happens. I'm going to collect 10 data samples, 10 data values, all right? And let's just say that my standard deviation ends up being 3.5, all right? That's my standard deviation. Or wait, I'm sorry, that's my variance. All right. I know that if n equals 10, then the degrees of freedom is equal to 9. I need to slow down because I'm starting to say silly things. All right. Now, I'm going to build one of these confidence intervals out around the variance. And then when I'm done with the variance, I'm going to get to my standard deviation. All right. Now, but let's talk about this for a sec because I want to make sure that you all get this. I'm going to build a 95% confidence interval around sigma squared. Now let's remember just real quickly in case you got up and had to go to the bathroom or whatever. Remember, these form this chi-squared, or it's an F curve under some very specific circumstances. Now, the idea behind the confidence interval is still the same. In other words, when I find this chi-squared left and I find this chi-squared right, the probability or the area underneath this thing is 0.025, and the area under this guy is 0.025. The area under the whole thing is still 1. The problem is the asymmetry doesn't allow us to do that fancy schmancy that z alpha over 2 or t alpha over 2. So we have to use a different process. All right, so what we're going to do is we got our n. Notice the formula is actually really simple. You need n, you need s, you need chi-squared. So when we're doing one of these guys, we're going to do chi-squared left, and we're going to do chi-squared right, and we're just going to dig them out of our formulas. So bear with me here for just a sec. I have this cool little drawing right here. I'm going to do it actually on both of the tables just so you can see it, and this won't take very long. First thing that you want to do is identify your degrees of freedom. So there are my degrees of freedom again. Now remember, if I'm doing 95% and this is 0.025, this table reads to the right of the critical value. So if this is 0.025, then everything to the right of it, way out here, is 0.975. So I stumble onto my chart, I go down to 9 degrees of freedom, and I end up with, what do I end up with? 2.7. All right? Now, it's easy when I'm over here. I know this is also going to be 0.025. So I go over, because my chart reads to the right, 0.025 degrees of freedom. I cruise over to here, and I get 19.023. So this is 19.023. And again, those of you out there might say, wow, Ripley, those are big numbers. Well, remember, they're variances, so you've got values which are squared. Let me change back here. Now, all that I have to do is throw this in my formula. I know that sigma squared is going to live between n minus 1. Hey, is that degrees of freedom again, right? 9 times 3.5 times 3.5 divided by the big number, because I need the small value to be on the left-hand side of the interval, 19.023. And I need the big number to be 9 times 3.5 divided by 2.7. That's why I'm dividing by the smaller number. And then I'm going to throw this guy in my handy-dandy. Let's see, 9 times 3.5 divided by 19.023. And I end up with 1.66 less than sigma squared is less than, the second entry, and divide by 2.7. 2.7, and I end up with 11.67. All right, and we would write this, if I wanted to write a confidence interval, I would write this as 1.66 to 11.67. All right, now, but really what we're interested in, remember, the standard deviation. All right, so I know that sigma, according to this confidence interval, I know that sigma is going to be, what, square root of 1.66? Just throw that in, I get 1.29. 1.29. And if I take square root of 11.67, I end up with 3.42. All right? My standard deviation in a 95% confidence interval is going to be between 1.29 and 3.42. I can be 95% confident. But if I do this a whole bunch of times, I'm going to end up with these values. Now, what happens if I want to be more confident? What happens if I want to be 99% confident? All right, let's go through that just real quick. All right, so we got the same thing. Lost my dingle here. All right, n equals 10, df equals 9. I want to be 99% confident. All right, just humor me for a sec. All right. Looks, ooh, they're getting better, aren't they? They're getting prettier. I just shouldn't draw this part. Now, in this case, since I'm 99% confident, then what I'm going to have here is a 0.005 and a 0.005. So let's change colors again. When I do that, when I go to start looking for this chi-squared to the left value, then this is going to be 0.995. Okay? So let's do that real quick. If I hop out of there and I go to this, let's see, if I go to 0.995, notice how they set it up, because sort of the union standard is for us to either have a 99, a 95, a 98% confidence interval, et cetera, et cetera. So I know that chi-squared on the left is going to be, for degrees of freedom, 1.735. 1.735. And chi-squared, I should have done the fancy chi-squared on the right, is going to be for 0.005, 9 degrees of freedom. Look at that. It's 23.589. Now remember, over here, let me go back here. I'm not going to go through the whole painful process, but look. Chi-squared left there is 1.73. Chi-squared left here is 2.7. So what I've done is I've shifted down, just like you would expect. I would also expect if I wanted my confidence interval to be bigger, right? Remember, the more confident, the bigger the interval needs to be. I would expect my chi-squared right to shift up. Well, I went from 19.023 to 23.589. All right, enough of confidence intervals. In the next chapter, we're really going to put everything together, and we're going to start being able to test stuff. We're going to be able to start calling people liars, well, with a 95% confidence level. I hope you enjoyed. This is I love this little string of sections because they're a lot of fun and they get really, really useful. Okay, so I'll see you in the next.